Good morning, everyone. My name is Jan Janak, and I would like to talk to you today about one of our existing research projects in the Internet Real-Time Laboratory at Columbia University. The project is at the intersection of WebRTC and Internet of Things systems. The name of the project is SECE. SECE stands for Sense Everything, Control Everything, and the general idea is we would like to design the building blocks for distributed end-to-end programmable IoT applications. If you are familiar with the IoT frameworks that are available today, most of them deploy an application to cloud infrastructure, and every individual IoT device would connect to the cloud infrastructure and transmit all the data there for processing. Our goal is to design applications using a slightly different model called computation follows data, where instead of deploying an IoT application to a central cloud, the application gets broken down into independent modules, and those modules will be deployed to the devices themselves. This approach has some benefits. For example, it is possible to design security and privacy-oriented applications this way because you don't have to transmit your sensitive data to a cloud. It scales better, and the system is more resilient because it does not depend on the availability of the internet connection. But there are also challenges. For example, it's hard to design applications for such systems. It is hard to develop reliable applications that deal with concurrency. And it is very hard to design a distributed application if you do not have all the hardware available. So the system architecture for SECE looks something like this. In the upper left corner, there is an application repository, which could be something like GitHub or GitLab. And the application from the repository gets deployed to cloud-based infrastructure that is running on Amazon Web Services. A SECE framework running on Amazon Web Services deploys application modules to individual devices. So every device that you see in this picture, which has this red rectangle over it, is programmable over the network from the cloud. And tiny little pieces of code get deployed to these devices by the framework. So for example, you can program an Android tablet, you could program a laptop, a Raspberry Pi, or a smartphone. What are some of the use cases for distributed IoT applications? For example, you could implement an Internet PLC. PLC stands for Programmable Logic Controller, which is usually a piece of hardware being used in industrial systems, where you would typically have two devices, one equipped with a sender and another one equipped with with an actuator. And the device equipped with the sender would stream sender values to the other device, and the actuator gets controlled using the data. This is a very common scenario in industrial systems. There is where people very often use something called PID controllers, which stand for proportional integral controller. SECE makes it possible to develop such applications on top of ordinary devices, for example, Raspberry Pis or Arduinos or tablets equipped with a web browser with JavaScript support. Another use case is a privacy-oriented application. Imagine that you would want to build a security-oriented camera. So for example, you install a camera in your living room and you want to implement some sort of Internet of Things applications on top of that, for example, a baby monitor or a motion detector. There are existing products on the market which would stream the video from such a camera to the cloud for processing, but that is obviously not very secure because as soon as the data gets out of the camera into the cloud, you lose all control over it. The goal of the SECE framework is to make it possible to implement a privacy-oriented camera where the framework would install a tiny little application on the camera itself, and the application removes all the privacy-sensitive data from the video stream. For example, if your target application is motion detection, you can pre-process the image in such a way that it's no longer possible to recognize people or faces. You could still have a privileged display running in the same local network, as you can see in the image on the right, which would be able to access the raw stream, but the only stream that the camera would send to cloud infrastructure is very limited and pre-processed. Designing distributed application like this means that you have to work with a large variety of devices. This slide shows some of the devices that we have used in very simple projects in our lab. So it ranges from tiny little devices like Zigbees to Arduinos to Linux-capable computers like the BeagleBoard. Where does WebRTC come in? As I mentioned before, it is kind of hard to design applications, distributed applications, if you do not have the hardware available. So we have been trying to figure out if modern web technologies, namely WebRTC and HTML5, would help with this. Some of the design goals for the framework that we have been trying to develop are that we would like to enable device-to-device communication. We would like to make at least some limited form of prototyping possible without having all the hardware available. And we would like to be able to run all this on existing devices, including laptops, tablets, equipped with a browser, and so on. So we have been developing a JavaScript-based framework. Here you see an example of the user interface that the framework provides. This picture shows a tablet that is running a JavaScript application in full screen mode. This is a virtual control panel implemented in JavaScript. The components on the panel emulate real physical devices such as LEDs, sliders, analog gauges, and buttons. Every single device on this panel is essentially a JavaScript object which is accessible over the network. So that means you can subscribe to the state of a button, or you can send a command to turn the LED on or off. So this user interface is designed to run on a tablet. There are multiple modes of operation. For example, you could display the same user interface on multiple tablets. If you have multiple tablets, then you can synchronize the state of these panels across multiple tablets, or you can configure the virtual control panel to be only displayable on one particular device, in which case it will store all state locally in web local storage on that device. The more interesting scenario is where you would have multiple such devices. In that case, we wanted to be able to set up direct network sessions between such devices, so that, for example, a button running on one device could directly control an LED or some other virtual port on another device. And so we have been using WebRTC data channels for this, where multiple devices connected to the same network dynamically create WebRTC sessions between them, and you could then use data channels to obtain the state of a particular device or to control it. Since data channels are essentially just streams or sequences of packets, you could run any application level protocol on top of that, including MQTT, COAP. Here is what the network architecture looks like. So every device has a WebRTC peer and a WebSocket client. When the device is added to the network, it connects to a WebSocket server for signaling. We use a custom JSON-based signaling protocol for that, and it registers itself to the network. As soon as there are multiple devices within the network, they discover each other via a central registrar and then start setting up dynamic WebRTC peer sessions. So for example, if device A wants to obtain some information from one of the elements on the control panel on device B, it will create a WebRTC peer connection to the device and obtain the data. It's also possible to connect to this network from devices that are not WebRTC enabled, such as the box in the bottom right corner, via a simple HTTP to WebRTC proxy. All right, so the virtual control panels described on the previous slides sort of led us to emulate or interact with devices, but a problem in distributed IoT systems or applications is that very often we do not have all the devices available when we start prototyping the application. For example, if your application is interact with 10 Arduinos or is distributed across a bunch of devices, you're unlikely to have all devices available. So we have been looking into the possibility of emulating some of the simpler IoT devices in the browser and in JavaScript. Obviously, this approach doesn't work for bigger devices like the Raspberry Pi, but it's quite suitable for smaller ones like Arduino, Teensy, and many of the existing small devices. The general approach is that we would like to take an application, let's say, written in the Arduino C++ language and find a way to directly emulate and run that application in the browser. This has been inspired by a project called the Internet Arcade. I'm not sure if you heard about that, but the Internet Arcade is an attempt to preserve all arcade games for future generations. So there is a website, and if you go to the website, you can play very old games like Pac-Man or Galaxy Invaders or anything that used to be available on real big hardware. This is what this looks like. So on the left, you see an arcade machine that implements a Space Invaders game, and these days it is possible to run the software from that arcade machine in the browser. The browser window is on the right. The idea is that you take a RAM image from the arcade machine, design an emulator for the machine and run that in the browser so that you can run the application unmodified without having to change the source code or do any modifications to it. There's a large collection of those, and the picture here on the left shows the structure of what the Internet Arcade emulator looks like. It takes a RAM image of the game, runs that in a simulator called MAME, which is a multiple arcade machine emulator written in C and C++. That gets compiled down to JavaScript using Emscripten. Emscripten is a C to JavaScript compiler, and eventually the resulting code is deployed to the JavaScript environment in the browser. Now, if this works for arcade machines, we could probably use the same approach to emulate IoT devices. So we have been working on emulating the Arduino and Teensy devices in JavaScript this way. So we take an Arduino or Teensy application written in C++, compile that through Emscripten, and the resulting code gets deployed to the browser and runs inside the JavaScript environment in the browser. Here, this picture shows the entire JavaScript framework which runs in the browser, which implements both of these features, the virtual control panels and the emulation environment. The rectangle on the left is the device runtime context, which essentially is a separate background JavaScript thread implemented using web workers that SECE can deploy applications into. So you can install JavaScript applications inside this environment. Every application will be given its own background thread. That application can be directly implemented in JavaScript, or it could be the result of mscripten in form of asm.js, which is a subset of JavaScript which essentially uses JavaScript as bytecode, which means you can download an application that connects a virtual sender to a virtual actuator, and this application will run in this context. There is a peer connection manager which takes care of setting up WebRTC peer connection to remote devices. And then the rectangle on the right shows the user interface context, which takes care of rendering the user interface and letting the user interact with the device. So this is what implements the individual widgets on the virtual control panel, and there is a communication channel between the user interface context and the device runtime context. So in summary, SECE has been our attempt to design a framework for developing end-to-end programmable prototyping applications designed mainly for privacy and security. As we go and try to implement some of these applications on top of the framework, we figured out that it's really, really hard to do that because you very often do not have all the hardware available, and designing distributed applications is hard. So we have been working on integrating HTML and WebRTC and JavaScript into the framework so that we can run or prototype a very early version of the application directly in the browser. We have implemented virtual parts modeled after real physical parts in JavaScript. There is a library of the most common types, and the library is extendable, so anybody can design a JavaScript package and implement additional parts. We use WebRTC data channels for direct device-to-device communication. So for example, if you have multiple devices, the parts running on those devices can communicate directly without having to go to a cloud infrastructure. And we have been working on emulating IoT devices in JavaScript. So far, we have a very early implementation for the Arduino, so we are able to run a simple Arduino program inside the browser, and then the individual parts of the Arduino platform then can get connected to the virtual parts. So you can, for example, press a button, the button is connected to one of the parts on the Arduino, and the program emulated in the browser would switch a LED or communicate over the network using WebRTC and so on. And with that, I'm finished. I'd be happy to take any questions you might have.
The PID controller that will be controlling the IoT devices, how are these commands from this controller exploit the WebRTC portal?
So you have two devices, a device A equipped with a sender and device B equipped with an actuator. These devices set up a WebRTC data channel connection, which is essentially just a stream connection. And you can run any algorithm, any application level protocol on top of that. So we are currently using a very simple JSON-based protocol to stream periodic updates from the device equipped with the sender to the device equipped with the actuator. So for example, if one of the devices has a temperature sender connected to it, it could be programmed to send temperature measurements every few seconds to the actuator device, and the actuator device will control some physical process based on that data. So WebRTC in this case is used only for transporting a sender measurements, but you could use it in the same way for much more complicated scenarios and much more data-intensive scenarios. For example, if the sender device was a microphone and the actuator device was a speaker or some other media-oriented device, you could, instead of data channels, use the WebRTC media streams based on RTP. But the general idea, the reason why this uses WebRTC is mainly to make sure that the latency, the round-trip time between the two devices is as short as possible. Because you don't typically want to go all the way to Amazon Cloud and back for these types of applications.
I realize you mentioned that you use virtual ports here. Is there a limited number for the virtual ports, or?
You mean this?
Yes. Yeah, when you talk about the virtual ports, is there a limited number of virtual ports or unlimited?
It's definitely limited by the amount of memory that you have in your device. I don't know what the limit is. So we have had tried control panels that had tens of those. So I'm not really sure where the limit is. The JavaScript application that actually implements this is somewhat memory hungry, because you need to create multiple WebRTC sessions, and that is going to eat a lot of memory. So the limit is your memory. On modern day devices like the tablet in here, it's unlikely that you'd run out of memory, but it might be an issue on a smartphone where the JavaScript environment is much more limited.
Okay, thank you.
That's going to be a different application, though.
Yeah,